Okay, so hi everyone, thanks for being here and thanks the organization for letting me doing this talk. So today I want to talk about my latest work, which is about limit-sketchable infinity categories. I'm David, and this is joint work with my advisors from the University of Barcelona, which are Carles Casacuberta and Javier Gutiérrez. So, I will first do like an introduction to the main ingredients of my talk, and then we will like get to work and see a little bit. So first, for an introduction of things that you may or may not know. First of all, my main ingredient in this talk is limit sketches, which has already appeared at least in one talk. I could go to all the others parallel, but at least in one of the ones this morning, where basically limit sketches allows us to model in some way essentially algebraic theories. So a limit sketch is basically a pair of a small category and a set of cones in that category. To give an example to illustrate at the same time, we will consider the small category A, which is generated by 4 objects, 0, 1, 2, and 3, and there is a commuting square, okay, and the freely generated category there, so I didn't paint the identities or whatever. So this is a trivial sketch in some way, where our commuting square is a cone with apex the object 0 and diagram all these other objects, and if we take this cone and our small category, this will be in fact a simple sketch. What we can make with a sketch, if we have a limit sketch, we can take its models, which are basically functors from our small category to the category of sets, which take our cones to limit cones in the category of sets. So in this example, we will take a functor f, which goes to sets. It selects 4 sets, and it has to send this cone to a limit cone here, which is basically amounts to a pullback in the category of sets. So for this simple sketch, the models that we generate, the theory that we generate, is the theory of pullbacks of sets. Okay. So let's go by the second ingredient, which is presentable categories or presentability in general. So this is basically a way where we can have a locally small category, but which is generated in some way by some small subcategory. So first we need to define what is an accessible category, which is locally small, and there is some type of nice colimits, which are the kappa filtered, and there is some small full subcategory of small objects, which are the kappa compact, such that though this full small subcategory generates all the category by kappa filtered colimits. If we have an accessible category, we can define a classically called locally presentable, but nowadays normally only presentable category as an accessible and complete category. So examples, the main categories considered normally are presentable in some way, for example sets, groups, implicit sets, etc. There are some examples of well-known accessible but not presentable categories like fields, Hilbert spaces, and there are many more. And it's not so easy, at least for me, to find non-accessible categories, but one example will be the trivial or naive category of topological spaces without any reduction. And that's more or less the classical theory. And the last ingredient of my work is working with infinity categories. This is a one-slide introduction for anyone that maybe doesn't know anything. So this is not a definition of infinity categories, because we need to choose a model of infinite categories, but this is like an abstract idea where we have a collection of objects and then a collection of n morphisms between n minus 1 morphisms for all n. So we will have 1, 2, 3 and up collections of morphisms. Then we need to define composition, identities, associativity up to a higher morphism and weakly. And finally, we ask for this to be an infinity 1 category, that all the n morphisms with n greater than 1 are invertible up to higher morphisms. So everything weak. And here I had a drawing, but it's not very important. So what I work on, the idea is returning to some classical theorem, which in some sources was called a representation theorem. First, I didn't say a category is limit-sketchable when it's equivalent to the category of models of some limit sketch. And then the theorem of interest is that a category is presentable if and only if it is limit-sketchable. So I have presented those two ingredients, which in the definition were totally different, and in fact it seems like they are totally related. This result was proven by Gabriel and Ulmer in the 70s, and then I have mostly worked by reading the revised version of this result with much more in the book of Adamek and Rosicki. And here we reach my goal. My goal is basically to generalize this result to infinity categories. There has been work with model categories, and there have been other works in other directions in this field. But I wanted to try to do this. So, let's get a plan for the rest of the talk. First, I will generalize the limit sketches to limit infinity sketches. Then I will make some small comments about presentable infinity categories. They are much well known than the infinity limited sketches, but I think there are some comments to be made here. And lastly, I will comment some observations and if I can get or not this representation theorem. So, first part. Let's go to the limit infinity sketches. First, we will need to define limit and colimits in the infinity context, but I haven't given any model, so I give again. This is a definition that I like a lot because it works in one category and it works in mostly all models of infinity category, with some exception. So we consider C to be an infinity category and I to be a small infinity category. Then we have always a constant diagram on any object, which sends all the information of I to this particular object of C. And then we can define a cone over a diagram, which is basically an infinite functor, as a natural transformation from this constant diagram to our diagram D. This definition always holds, and then we can define a limit cone of our diagram D as basically a cone from an object which we will call limit of D, such that it has the expected natural property, which is that any natural transformation from here to here for any object, which are basically any cone of D, and need to have a morphism from X to the limit. So it says that, but in a weak way, asking for a weak inverse of this morphism. Okay, and for cocones and colimit cocones, we go to the dual, to the opposite infinite category, and we get it done. So then we define the limit infinity sketch, which was defined, I think, first by Joyal in the notes of Barcelona of the CRM, as a pair of a small infinite category and a set of cones. So it's the same definition as before. Here I give a little more precise definition of model, where we take C to be only complete in the limits that we need, and then we can ask for models in any C. So it will be a model. It will be a functor sending cones to limit cones to any C which has those limits. And I will denote mod of the sketch on C for the category of models on any C, and mod of the sketch for the category of model in spaces, because here in infinity categories, where we before put sets, we are now putting always spaces as the infinity category of homotopy types. Okay. And then we have the same thing, so we have a concept of limit infinite sketchable, which is an infinite category which is equivalent to the infinite category of models of some limit sketch. And one thing that I didn't talk about earlier, that an infinite sketch can be normal, which basically means that all the cones of L are proper limit cones in A. So then this will be more what is called a limit theory, I think, or yeah. So some examples. We have the classical or more classical examples which come from Lorry theories or generalized Lorry theories, which are algebraic theories or infinity algebraic theories. They are very old. There is many examples of these, like monoid objects, commutative monoid object, group objects, R modules. And when we take them in the infinity world, we get up to homotopy coherent constructions, like infinity spaces, or infinity groups. And there is a nice paper called Homotopy Varieties of Rosicky, which basically prove that all these are presentable. Then there is recent work that I think it was presented in an international category theory conferences like 2 or 3 years ago by Chu and Hausen, which is called Algebraic Patterns, which is very close to an limit infinity sketch, and it allows us to define more things like category objects or operand objects, which in this homotopy coherent mind they are called Siegel spaces or Siegel dendroidal spaces, and there is much more examples like n categories, and there is plenty here. Then we have some examples that cannot be modeled in any of those two cases, but can be modeled as a limit sketch. For example, we can take a spectrum object, which also doesn't make much sense in the one categorical case, and it recovers the homotopy theory of spectra. And then we can add conditions to previous sketches to get univalent category objects or univalent operand objects, which recover complete Siegel spaces and complete dendroidal spaces, which are basically the homotopy theory of infinite one categories or infinite one operands. Then the last of my examples is infinity shapes. It's the only example that I have that the A category it can have full infinity levels and complexity, and it's also a nice example that I think that cannot be summed up on the other cases. So I will only give some details in the category objects example to give a review of how all this is done. So we take a complete infinite category, and we will take cones for every n in our small category, which will be the delta op category. And basically this will be the cones that we have. We have the typical diagram here of a Siegel condition, and then we put the n of this alpha n as the apex. Then the sketch of this small category with the set of all these cones is a limited sketch, and the models are simplicial objects in our category C, such that they have the Siegel condition. So basically the models are category objects on C and Siegel spaces, as I said earlier. So how can we improve this to get complete Siegel spaces or univalent category objects? We basically take LS to be the set of cones as before, and we add a new only one cone called beta, which is basically this cone drawn here with all this red diagram and this apex. And we can make a translation of this. It's only in the op, it's only applying the F and then compute some fiber products, and we obtain this pullback. Then it's not obvious that there is work of I think it's done. It was done by Nimarasek, but there was an older reference that I don't remember, that basically this condition is equivalent to the completeness condition of a Siegel object, and then we recover the univalent category objects or complete Siegel spaces. So these are some examples of limited sketches, and let's get to the presentable infinity categories. Then here I have, this is the most technical part, that to define accessibility I will need to define all these concepts. So we can define an object of the infinity categories of spaces to be small if all its homotopy groups are kappa small for some kappa. Then we can have a definition of kappa small, I left the kappa there, such that the home spaces for every two objects are kappa small as spaces, as here, and then also the isomorphism classes of objects are kappa small. This is also, in fact, also model independent in some way definition of smallness. And then we need a definition for filtered and compact. Category is filtered if for every kappa small indexing category and every diagram there is a cocone, sorry. And then a kappa filtered colimit is basically a category admits kappa filtered colimits if it admits k-indexed colimits for kappa filtered categories. Okay. And finally, we define an object to be kappa compact if the home space functor preserves kappa filtered colimits. And that's all the technical. And then we recover the one categorical definition of accessibility where it's all the same with some infinity things. But here in reality we're doing a little bit we're cheating a little bit because the usual definition of accessibility in the infinity context is this other one where we take the free completion of a small category under kappa filtered colimit, which is called int of L, for some kappa and some small infinite category. But this was shown since beginning of infinite categorical things that in fact the two definitions are equivalent, so we recover the same concept that we have in the one categorical case. So then for presentability it's the same definition as before, and we get many examples. Every one category which is presentable, the category of the spaces is presentable, and every functor category and every infinity topos is presentable. So for my last section, let's see what we managed to do with the representation theorem. We basically prove the theorem by the two separate implications, because one is give us a little more information. For starters, if we have a limit infinity sketch, we prove that the category of models is presentable in spaces, and then also that if we have a presentable infinite category C, there is always a normal, which therefore like realized limit infinity sketch such that it's equivalent to the models. These are also reproduced how it was proven in the one categorical case. And the ideas for the proofs are a little bit following the initial, the classical proofs, but we have gone in different ways. In the limit sketch that we construct here, for example, is the same, but proving this equivalence is totally different. And in this case is pretty similar, where we basically build up a localization, but in this case it's an infinity localization, and then use one well-known theorem of existence of localizations. Therefore we get several corollaries. The thing that we want to prove, we have the if and only if that we announced at the beginning. Then we also have the same version but for any C, so if C is presentable, then the models on C are also presentable. And finally, if we apply A and then B, we obtain that for each limited sketch there exists a normal limited sketch with the same models. But this only works if we take models on spaces. And our first sketch can be finite and nice, like the ones that I show you, but this one will be small but not nice. So, to end, I want to speak a little bit about my work in progress. Now I'm basically trying to prove the next result in this direction, which is forgetting about the limited sketch thing and talking about the sketches. And a sketch is basically a limited sketch where we add also a set of cocoons, and then we send these cocoons to colimit cocoons by any model. There is a result which was first proven by Lair, then by Mackay-Paré, which is a more modern notation, and finally it was also redone in Adame-Krosicki. that accessible categories correspond to sketchable categories in general, and therefore we think we are very close to having this proof also. And it's similar to the previous case in the sense that there is some strategies that work and some where we take like new approaches. And then also in one summer school that I was, I meet Emilio Riel and I meet the people of a proof assistant called RESC, which are trying to work in synthetic infinity categories, which are model-free and types theoretical approach to all these higher categories setting. And I'm like trying to learn and trying to formalize things, so maybe one day I can like formalize my work in one of those proof assistants and check that I didn't make some mistake or something, I don't know. And some only reference that I cited during my talks, so the first Gabriel Ulmer thing, a little bit the notes of Virgil, and the more recent work of Chu and Rune. So thank you everyone for listening, and yeah.
Okay, any questions? Yes.
Have you constructed like full equivalence between the category sketches and the category equivalence? Have you constructed an equivalence? So you sort of told us how to go in each direction, those two directions form an equivalence together.
Yeah, I don't have the equivalence. I have the two directions. Yeah, I'm not working with the infinity category of limit infinity sketch in the sense that I've proven that like the objects, not the. I have not studied the morphisms. This is also a work that I have pending, but I haven't checked it. I don't know what it is. I see this Gabriel Ulmer duality, but I always see it in the context of finitary presentable and finitary. So I don't know if it works in the general case.
Any other questions? Yeah.
So you talk about the spectrum objects that were an example. So can you say something about that example?
Yeah. It is my favorite example, but because we were in category theory, I choose the category object. But yeah, we basically took like a sketch which is something like that, where like an infinite thing like that, where the levels. So here we have to put a category in things, but let's imagine that this is already the model. And then we recover here like the levels of the spectrum. Okay. And then here we send all these objects to the final element, and therefore all those are pointed. And we first have the pre-spectrum, which basically we do this and don't touch anymore, and then we can take this pullback and put here the usual definition like this, and there is a morphism like this, and then we add more cones to make this thing an equivalence. So then we have this, and this basically recovers all the construction. We have to take also negatives, and yeah. But
spectrum objects in something.
Spectrum objects in any infinity category, and in particular, yeah, if you take spaces, it's a spectrum. Yeah. And it's really nice. This construction is not ours. The other last three are ours, but this one was already in Joyal nodes. I think that Joyal nodes are the only source of limit sketches applied to infinity categories that I found, and this was one of the motivating examples.
Question this, the nerve of this presentable category is going to be presentable in the infinity setting, right?
But what?
You said like the nerve of a presentable category is also presentable.
Yeah.
Is it an even only if?
Yes.
Okay, and then so top as a category is not
Yeah.
accessible, but the space is, in the infinity sense, is, I assume, because
Yeah, yeah.
different nerves.
Yeah. Yeah.
Should I interpret it as that it's a nicer setting to look at?
Yeah. But when you take top, you're not taking the one nerve. You take the the hammock or localization, and then the coherent. But and to do that, you need a combinatorial model structure, and to do that, you need not top, but some restricted, nice
Right.
topological. Yeah, if you take a nice category of topological spaces, then it's presentable. Yeah, it's all that you want.
Yeah.
I was wondering whether you were using a specific model of infinity category, or you had a more agnostic approach in your proofs.
Yeah, we tried to have. We made a seminar about Emily Reals approach, and we tried to be as model free as we can.
Mm-hmm.
But in reality, we are using quasi-categories, I have to say. But I will say that 99% of the proof is model free, and there is some things that I'm citing things from Luri that I think that they are, by things of Emily Real, I can use them, but it will be nicer if I had like all the thing. Yeah. For me, that's also the excuse of doing it in Dresk or something like that, is also to try to redo these little black boxes that I don't know if they are model free.
Any other questions? Okay, let's thank David again.